So I came outside here to test this in the evening. There was a massive heat wave. It was 35 degrees during the day. So let's see if it turns on and connects to the GPS.
So I had the idea to make a device that points to any place on the map. Initially, I thought I could use LEDs to show which direction to go, but I thought a compass would be a lot cooler. So I opted for the crazy idea to use 4 coils in this configuration with the compass in the center. So let's open this up. So here you see the 4 coils that are wound on these brackets, and the compass in the middle. That was like an old compass I bought at the thrift shop. And then the bottom houses all of the electronics. So we open this up. It's battery powered by a single cell LIPO. Then there's a microcontroller, so I used the ESP32C6 from Seed Studio, I think. Then, of course, for navigating with the compass, we need a GPS module. So I have like the basic GPS module. And then I used this IMU on the bottom here. That has the accelerometer gyroscope needed to get this thing working. To get the USB port out here, I just used this extension cable. And of course we need to somehow drive the coils. So the best way to do that is to use a simple H-bridge that is normally used to control motors, like for a cart with 2 wheels. But I just hooked up both of these in parallel, like these 2 together in parallel and these 2 together in parallel. So, and then I can use a 2-channel H-bridge to run the thing. So this configuration of coils is actually called a Helmholtz coil. But this is not an ideal Helmholtz coil because the magnets are way smaller than they should be. But for my purpose, it still works out. So these always ones opposite are wired in series. And then I can control using PWM how strong the field should be. And then I can make an arbitrary magnetic field vector to just point the needle into that direction. And since I'm using an H-bridge, I can also have negative amounts on the coil. So the current is running in the opposite direction, and then I can basically choose any direction where I want to face this coil. So these coils each have around 150 turns and these specs. And they're wired such that they produce around 2.5 times the Earth's magnetic field. Since the needle already points in the direction of Earth's field, which is around 50 millitesla, we actually need to have stronger magnets than that, such that we can overpower the Earth's field if we need to go in the other direction, for example. Also, another design choice is what I learned later on is to put this GPS module as far away from any metal as possible, and also water, because I think there's water in here or some other substance. And these signals are actually attenuated by water a lot, and also are like reflected by a metal that's close to the sensor. So now it also gets absorbed or reflected by the battery, and the battery is also around 4 centimeters away from the sensor. And it doesn't matter that there is PLA plastic over the sensor because it doesn't affect the field. So up to this point I thought everything is very cool and this will work out perfectly. But I underestimated the amount of math and programming this would cause me to do. So, first of all, the coordinate systems. There are so many coordinate systems. So to actually know where the compass needle needs to go on our device, we need to somehow put it inside a coordinate system. So we have our axes X, Y, Z, and I will call this the body coordinate system. So that's the coordinates that the gyroscope, accelerometer, magnetometer use on the device. They're all on the same PCB, so they share the same coordinate system. To make it a little bit simpler, I'm also going to introduce a local coordinate system. So the local coordinate system shares the same origin, but it actually points is rotated in such a way that the z-axis points upwards. So gravity is down, and x points towards north. So let's say the Earth is here. Then we have this z-axis here. No, the x-axis here. And in this case, the y-axis here somewhere. So that's the local system. And to interact with the Earth, we also need the Earth coordinate system. So that's the one from this standard, which says that the z-axis is pointing to the Earth's rotation axis, and x is pointing towards the 0 meridian. And the y-axis is given by the right-hand rule. So we have these three coordinate systems. So if you want to find out which way our compass needle needs to rotate, we need to find a mapping between the body system and the Earth system. So to go from local to Earth is simple. We just use the GPS coordinates. Because then we can actually calculate where this position is. So we know where the device is in the Earth. And we can also find out which way the z-axis goes, since it's pointing upwards, directly upwards, so away from the center. And the x-axis is pointing towards the rotational axis of the Earth. To actually go from the local to the body system, it's a lot harder. So the position is given because they're the same, but the actual orientation we need to find out using an attitude reference system. So I think the scientific term is the attitude and heading reference system. And this is used in airplanes, in your phone, in drones, in VR headsets. All of those share those three sensors, the gyroscope, accelerometer, and magnetometer. Let's say we just have an accelerometer and a magnetometer. The accelerometer measures which way is down or which way is up, and the magnetometer gives us a direction of north. So we would have all of the necessary data to find our heading. But this method is flawed because the accelerometer is disturbed by movement. So if I just bump my sensor, the estimate goes way off. And same thing for the magnetometer. It is affected by all kinds of metals and magnetic objects, and also electronics. So that makes it very unstable to use this for navigation. So the trick is to use the gyroscope, which gives us the angular momentum of our object. And we can actually integrate those angular rates to get the rotation of the device. So that's actually where the Madgwick sensor fusion algorithm comes in, which is used to fuse all of these three measurements together and give us the best possible estimate for our heading. So that's what I'm using in this device. So there's one more thing which you may have caught. I cannot be powering the needle at the same time as I am measuring which way is north using the magnetometer, right? So I actually have to switch between them. So I use the magnetometer to measure north. Then I power up the coils for some duration. Then I stop, and then I wait for a little bit of time to let the magnetic field decay and that the Earth's field gets to a normal level again, which can be then sensed by the magnetometer. Then I do this over and over at such a fast rate that the navigation works fine, but also slow enough that these fields have time to decay and don't influence each other. And this works fairly well. And I also only do the powering if the button is pressed. So if I don't press the button, there's just normal measurement of the attitude. So one issue with using sensor fusion is the calibration of the sensors. So there are these called soft iron and hard iron sources that disturb the magnetic field measurements from the sensor. So they either skew the measurements along an axis or they offset it completely. But there is one really cool trick we can use to calibrate this sensor. So since the Earth's magnetic field should remain constant at where I am right now, we can actually just take the device, start measuring values, and just rotate it a lot. And after we have a few hundred measurements or a few thousand, then this creates this shape of the vectors that make up this magnetic field. And since we know that the magnitude of this field should remain constant, we can actually just take the shape and stretch it into a sphere that is centered around the origin. And this corrects the skewing and offsetting of this shape, and thus also calibrates our sensor. For this project, I wrote a Python script that takes in values that I send over serial to the computer, and then this Python script fits an ellipsoid to those values, and then generates a file containing the correct parameters that we can apply when using the sensor in the firmware of the device. But this didn't work. That's the issue. And I made one big error when designing this. So actually, when I calibrated the magnetometer for this device, I didn't account for the needle itself. So I calibrated without the needle and everything worked perfectly. But by putting in this needle from a compass, actually this needle generates such a big magnetic field while it's rotating that it disturbs the sensor that is mounted right underneath this needle. So it's actually almost around 80% of the same strength that the Earth's field has on the sensor. And this throws off our attitude system while it's trying to measure which way north is. So then I thought, I cannot calibrate it with the needle because the needle is moving independent of the device. So there's no way to calibrate away its influence of the sensor. So, and there's also no way for me to know in which way the needle is pointing because it's flying around all the time. Then I had an idea. I actually know which way the needle is pointing. So I know it should be pointing towards north usually. Or it's pointing into the direction in the way I am powering it through the coils. So I tried to measure this precise amount that the needle influences the sensor. For that I wrote a calibration script. This script goes through all of the angles in like 5-degree steps, points the needle in that direction, then stops and just immediately takes a measurement from the compass sensor. Now over in VS Code, I plotted these needle errors. You see these 3 color rings are made by running the test in 3 different orientations of the device. So the device always pointed in the same direction, but the magnetic field was read with different positions of the needle. and I rotated the device twice to give me 3 different orientations. But as we can see, weirdly this is not horizontal. I thought it would be horizontal, but then I later found out that might be due to the offset between the magnetometer and the needle, and the needle's dipole magnet shape. But here I got the idea to merge these into a single dataset to get more points by removing their mean. So here is the combined data. It's now centered around 0. And I also plotted the initial angle of the needle so that I know where the needle was pointing to. For example, the needle was pointing at 5 degrees in its coordinate system, such that I can reconstruct the correct vector afterwards. So I was trying a lot to fit an ellipse into this data set, and I didn't want to just try out using sliders. So I tried some various weird ways, which all did not work. But then I just thought, why not use torch? So the idea here is to have mapping into 3D that takes 2 features. And these are the sine and the cosine of the angle. And in my reasoning, I could take in the input angle, then use sine and cosine to get my feature vector, and map this into 3D. And this should be able to parameterize any ellipse. Since I also want to fit the face, I added this face parameter as an offset, and that's my model. Then of course I also need my necessary torch piping. And there you go. So we can see the triangles are the fitted model. So these are just points spread over this fitted ellipse. And our original dataset contains the circles. So to actually get this into the code, it's super practical to just write this automatically generated C++ file that then gets linked into the project. So I have this eigen matrix that just takes in, where it just replace the string with the actual values. So if we run this, we then get this file, coefficients, and here we can see our parameters stacked here. So it is a neural network, but it contains just 7 parameters. And then to actually compensate for the needle, so you only need to compensate when it's pointing away from north, because if the needle aligns with the magnetic north, then the magnetometer just reads the same field anyway. So then I do this case distinction, and here I compensate with the red field, the red field vector. Send this into this function with the current needle angle to compensate for this error. So I calculate this compensation just like in the torch network, but here I'm using the eigen numerical library to do this matrix multiplication.
So there you go. Let's see. And it seems to be working. Though I'm not sure how accurate it is. My spot is somewhere over there, and it seems to have locked on. So when I press the button, now it should point to north. I need to keep it horizontal. When I press the button, it will start pointing in the direction. So that way is north. And our path is almost into the same direction. So I guess that's the spot, and it seems to work. That's where I placed my pin on Google Maps. So, success. I have to hold it horizontal though, such that it doesn't get stuck while turning.
So that was it for this video. This was my first video on YouTube in this format, so if you liked it, then let me know and write to me what you thought was alright or what I should be changing in the future. I'm planning to make more videos on my weird tech project, some of them taking more time than this. So just let me know about any changes, and thanks for watching. So I will be leaving any links to sources and also my source code in the description. And the 3D model for this device is a bit of a mess, so I would need some time to fix it. But if anyone wants to have the 3D model files, I can also send them to you.